Okay, so I wanted to do a video on completing the square. Why? Because it's one of those skills that people need to be sharp on, especially if you're in university, you need to be able to do this skill. And also, it's kind of cool when you think about it in terms of things that are not quadratics. And also just visualizing it for quadratics is cool too. So what does it even mean? Well, let's compute the square on regular numbers, because you can do that. How about 50? Well, 50 is, as you can see here, 49, which is a square. It's 7 squared, plus 1. This is a square in this case, but that's not important. It's not always a square. So you get 7 squared plus 1. So 50, if someone said complete the square on 50, you don't have to say like, what the hell are you talking about? You can say, oh yeah, that's 7 squared plus something. Okay, and of course you can do this with any integer. Any integer is going to be a square plus some other value, okay? Or it's just a square. All right, so the same is true with quadratics. What do squares look like in quadratic land? Well, here's some samples. So first of all, you've got y equals x squared, which you should be able to identify is just this red graph. This is the standard quadratic, or the parent quadratic. The blue one, y equals x minus 2 squared. So this is a right shift by 2. And indeed, if you look at the blue graph here, it is right shift by 2. And then green. So we have a vertical stretch by 2, and then we have a reflection of the x-axis because it's negative. And then we have a left shift by 2. So that's green, and right here, left shift by, okay, that works great. And then for purple, it's going to be a little bit fatter because you have a vertical stretch of a third, or in other words, a vertical compression of 3. And then you have a left shift by 1. Okay, and boom, there you go. Now, what do you notice about all these squares? All these squares, no matter what you do for a square, if you do x minus or x plus or minus something squared, and if you throw a coefficient out in front, you're going to get something that lies on the x-axis. It has to be that way, right? To move it off the x-axis, you're going to have to do plus or minus something at the end of your function. Okay, but squares don't have a plus or minus at the end of the function. So quadratics, a square looks like a parabola that's touching the x-axis. Much like integers, a square looks like, well, it actually looks like a square. Okay, so notice how any quadratic you could think of must be one of these squares that has been moved up or down. In other words, it's been vertically shifted or translated. Okay, so every parabola you've ever seen is actually one of these squares that's been moved up or down. Like take this green one, for example. If you moved it down by 1, it would be here. But like every parabola, it may not look like it by the form it's been, if it's in its different form, like standard form. If a quadratic is in standard form, we're going to go through some examples. It doesn't look like it's a square, but it is a square that's been just moved up or down. Every quadratic is like that. So that's what we're looking for. Just like every integer is a square plus or minus some little bit. Okay, isn't that cool? That's awesome, eh? Okay, so let's take this one. This is a standard form parabola, and it looks like this. Okay, from this graph, if we have this graph, it's really easy to see that this is just the square x minus 2. Okay, that's the square that we're going to find, because if you just moved it up to the x-axis, it's just sitting right here. Okay, and that's what squares look like. They're the parabolas that sit on the x-axis. So with the graph, it's easy to see that the square we have is x minus 2 squared because it's right shifted by 2. Or some variation like, in this case, it's also been vertically stretched by 3. But we'll handle that later. We don't really care about the vertical stretch right now. We'll handle that later. But what if we don't have an awesome graph? That's really the question. How are we going to find the square if we don't have this picture? If we're just given the formula and we don't have the picture, how are we going to find it? Well, let's peel apart our function. Y equals this. How did I get this stuff here? I just factored out the 3 from the first 2 terms. You'll notice if I redistribute this 3 back in here, I'm going to get 3x squared minus 12x plus 9. Aha, that's our original function. Great. Remember, we don't really care about the vertical shifts or stretches. We'll figure that out later. That's why this 9 and this 3 are in red, because they don't really affect this square at all. Okay, it just changes the shape of the parabola and the position of it here, but that original thing that was squared is not altered by those values there. So we don't really care about them for right now. We want to match this, this is obviously the same thing here, to something that looks like y equals 3 times a square. So really when people say complete the square, another way to think of that is find the square. Okay, we're looking for that square. So let's play the game called find the square. So if our function looks something like this one, well, if we distribute this x plus a squared, we're going to get x plus a times x plus a. But if we then distribute this thing, we're going to get x squared plus 2ax plus a squared. Now, okay, this form we can kind of match to this form here, right? Because look, we have an x squared, we have an x squared, we have an x term, we have an x term, and then we have some surplus on this one. We're going to have to deal with that surplus later. If this is the case, so if we want this thing to match this bottom equation here, then two things are now certain. First, a has to be -2. Because this x term has to be equal to this x term, a has to be -2. It's forced. There's not more than that one option. The next thing is that in every case, we're always going to accidentally add a surplus of a squared. So these things aren't actually equal right now. So this thing, we want to match to this, it's not actually equal right now. We're going to have to subtract this a squared because it's surplus right now. Okay, so let's summarize a little bit. So this thing, which we started with, is easy to match to this thing. But then we need to subtract that extra bit to maintain equality. So really don't use this one. Use this one. Use this third line here, okay? And recall that the first three terms were designed specifically to be that perfect square, right? If we expand this perfect square, we get back to this one. That's how we found these things. We just forced it to be a perfect square. And then this minus a squared is just, we're taking off that extra surplus that we added on accidentally, okay? And now all you have to do, now we need to distribute the 3 like a boss. So there's two terms in these big green brackets. The two terms in the big green brackets are x plus a squared and then just a squared. So if you have 3 times that, then the 3 distributes into each of the terms individually. So you have 3 times x plus a squared and then 3 times -a squared, which just gives you -3a squared. And then the plus 9's just been hanging out there all along. So if we just skip from the beginning to the end, we get this thing, which we started with, is really this thing. Because this one is our goal, because this shows us, this reveals the square, okay? Where a has to be -4/2. So you always look at this value here, you divide that by 2, that's your a value, every time. Every time it is, okay? So this is our quadratic that we're gonna end up with. Now, let's check that we did it right. Okay, so this one is right shifted by 2 and then down by 3. And then there's a vertical stretch here. Let's go to our quadratic. Aha, it's right shifted by 2. Remember, that was our square that we wanted. We did want x minus 2. That's what we guessed at first. And it's been downshifted by 3. Okay? And then also it's 3 times steeper than it needs to be, right? If you go over 1, this is x equals 2, this is x equals 3. So if you go over 1, the regular parent quadratic, which is just y equals x squared, goes up by 1. But this one goes up by 3, so it's 3 times as much. So it makes sense that we have this 3 out in front here. Okay, so let's go through a few practice problems so that you can get a little bit sharper and actually use this skill. So let's say we're given this quadratic and they say complete the square, or AKA, as we now know, find the square. So it's a square plus something. Every parabola is, just like every integer is a square plus or minus some extra little bit. Every parabola is a square plus or minus some little bit. So again, we factor out this stretching factor here. We don't really care about that, and we don't care about the 9 right now. We get this thing here. Well, if you follow the pattern from before, that's always going to be x plus a squared minus -4, because the -4 is distributing to those two things. Remember, here we go. This is the 3 distributing to the two things. In this case, it's the -4 distributing to the two things. Everything else stays the same. Now we put a is equal to -2 divided by 2. So you always take this thing in here divided by 2. So in this case, it was a -2 divided by 2, which equals -1. Plug that in for a and clean it up. That's all you got to do. So that'll give you x minus 1 squared plus, because there's 2 negatives here, that gives you a plus. -1 squared is just 1 plus 9, and then you put that together, you get 13. So the square in this case was x minus 1. If we say find the square, you say it was x minus 1. When they say complete the square, they really mean return the whole thing as your answer. Okay, another one, maybe a little bit harder because there's fractions, although I love fractions, and you should too. They're just so pretty, and they work out so nicely. So let's factor out this -1/2 from the first two terms. Okay, so this works because if we go -1/2 times x squared, I generate the -1/2 x squared, thank God. And then if I do -1/2 times -12, I should get a +6, and I do. All right, so when you're factoring in a fraction like that, just think, what do I have to multiply this fraction by to generate this? And so it's -12 in this case. The 5 stays there, we don't care about that. You can skip immediately to this next step, x plus a squared minus -1/2 a squared plus 5, and a is going to be this number divided by 2, so in this case it's -6. You throw that value in and you clean it up. That's all you got to do. So we get x minus 6 squared plus 18 here, because 6 times 6, or negative 6 times negative 6 is 36. Times a half is 18, and then the two negatives equal a positive. Okay, plus 5, and that's where you get your 23. And then that's it. That's all there is to it. Okay, so hopefully that makes some sense. Hopefully that helps you practice a little bit of completing the square, but also hopefully you see what's going on, how every parabola is a square that's been shifted down or up, and you're just looking for that square. That's the behind the scenes. So I hope you enjoy it. Subscribe, like, and yeah, we'll catch you next time. Pieces.